Hi, and welcome to lecture 14. We're going to talk about regularization and renormalization, focusing in this lecture on the regularization procedure. Well, the whole ideas, which we'll discuss really shortly now, is based on the so-called Camel principle. If you don't know the Camel principle, here's a story. Long time ago, there was an old man, he was dying, and he inherited uh, his camel herd to his three sons. He said that the oldest one should have one half of the herd, the second son one third, and the youngest one ninth. Now the problem was that he only had 17 camels. Now the sons didn't want to cut camels in half or in smaller parts, so they didn't know how to proceed until the neighbor, the wise neighbor, came along and helped them by borrowing them one of his camels so that they had in total 18 camels, which then meant that they could take half of the camels, which was then nine. They could take one third of the camels, that were six, and then they could take one ninth of the camels, that were just two. And they could fulfill their father's will and gave the camel back to the neighbor. Well, it is just a small illustration how a simple operation of adding and subtracting the same camel, same thing, is not changing the fundamental expression but can really help us doing the calculation. Now, this would hold even if the number of added and subtracted camels would go to infinity. This trick will be used as well in the case of quantum field theory to get rid of a technical artifact, namely the divergences that appear when we go to higher order calculations. Now, let us first go to a simple theory that we didn't study in detail yet, but we have already briefly mentioned it. The interaction term of this theory is phi to the 4, so it is quite mundanely called phi to the 4 theory. It's a real scalar, which you see on this free Lagrangian as being just the Lagrangian of a one real scalar field. And there's an interaction phi to the 4 with the interaction coefficient lambda, which has obviously mass dimension 0. It's just a number. And there's a factor of 4 factorial in this coupling to account for an exchange of the external lines, symmetry of the vertices. The Feynman rules of this theory are similar to what we had learned. So the incoming and outgoing lines just give you ones, and they don't carry any arrows because this is a real field, doesn't carry charge. The internal lines are propagators, and they give just I over k squared minus m squared, where the m is the mass of this one field in the theory. The vertex gives the expected negative I lambda, where lambda is the coupling strength, and the fact that one can exchange these four possibilities in an arbitrary way in each vertex. So every diagram comes with a factor of 4 factorial that cancels the 4 factorial in the coupling in prefactor in Lagrangian. So the Feynman rule is just negative I lambda without any additional factors. Then we also have to integrate over loop momenta that are not fixed by external momenta. And there is another subtlety here, since we have symmetry factors, identical fields that can be exchanged in internal lines. We will have to take into account the symmetry factor and divide each diagram by a factor d that I will tell you in a second how to compute it. And it takes into account the double counting that we will get from using Feynman diagrams compared to the Wick contraction. So the Wick contraction combinatorics would give you the correct diagram, but using Feynman diagrams, we overcount by a factor d that we will have to divide out. And the rule to getting the factor d is if there are n ways of arranging vertices and propagators in a part of a diagram, in each subpart of the diagram. The external lines are fixed, but the internal lines can be rearranged. So if there are n waves of arranging the diagrams in this sub-part of the diagram, we get a symmetry factor di of this subpart that is equal to n, being the n ways of arranging vertices and lines. And the total symmetry factor is this product of all of those d factors of the sub-diagrams, which we then have to divide by. Let's see. I mean, this seems like a general rule. It might be not super obvious how to apply it yet, but let's have some very useful sub cases. For example, every propagator with the ends joined, essentially being a loop, that gives us a factor of 2. Every pair of vertices joined directly by end propagators then gives us n factorial, because we can exchange the direction basically of the propagator, and here we can swap the lines that are joining the two vertices in n factorial ways. So there are two rules that are easy to remember and are easy to use. Let's say the example here, we have a propagator. We have a propagator that goes back to the same point, essentially one loop, and that gives us this symmetry factor d equals 2. Simple. Now we have two loops joined at one point. We have d1 with d1, which is 2, d2, that is 2, and we can swap the whole diagram, and we have an exchange symmetry. So we have 2 times d1 times d2, being 2 to the third power, being 8 for this arrangement. Now we have this diagram. It's called the Saturn diagram because it looks like Saturn. And here we have 2 points joined, 2 vertices joined by 3 lines. That gives us 3 factorial. Good. Now we have this diagram where we have, this is actually very similar. We just add the external lines. So we have vertices here. So each of them is a vertex, two vertices. We can look at each sub-diagram. We have 2 vertices here joined by 2 lines. It's a 2 factorial. It's a 2. Here's another diagram with 2 vertices joined by 2 lines. So there's another factor 2 factorial. And we have this swap symmetry. So we have 2 times 2 factorial times 2 factorial. It's a factor 8 again. So whenever we have then this diagram, we have to sum over all possible momentum assignments and then divide by this total symmetry factor d of the diagrams. Then these are all the Feynman rules for this theory. Now we are interested in the matrix element of the theory, where we have n particles coming in, n particles going out, and there's this T transition matrix element. If you remember, the definition of it was the scattering matrix was 1 plus I 2 pi to the 4, then the momentum conserving delta function, and then this transition matrix element. Now we're considering matrix element where the pi are not necessarily equal to E, the zero component of the momenta are not necessarily equal to the energy of the particles, so the particles can be off shell. Now I'm going to tell you the recipe how to handle diagrams in general of this type. If we have those loop integrals over momenta that are not fixed by external momenta, they are so-called loop diagrams, we can handle them by this Wick rotation. Wick rotation means not the Wick contraction, but the Wick rotation, the replacement of the energy, the zero component of the momentum by I times the zero component. I, so if we have k naught, we have ik naught after the Wick rotation. You can think of it as a rotation from the real axis towards the imaginary axis in the complex plane, but it's just a trick. So for the 4 momentum scalar product, we have k squared, usually we have k squared as k naught squared minus k vector squared, But now we get this I that gives you a negative sign in front of this component. So we have a negative k naught squared, negative k squared, which gives us a total minus sign times the Euclidean norm of the 4 vector. And this d4k gives us an I d4k Euclidean from this factor. We just factored out the I out of the measure. Now, furthermore, we have to introduce a regulator to make the integrals finite, and we will use a momentum cutoff. So we integrate only over momentum, absolute momenta, which are smaller than lambda, absolute Euclidean momenta. Well, now we transform the loop momentum integral to an integral over the 4 sphere. So we have a function just of the Euclidean momenta, d4k. We write it as a integral over dk, where k is the absolute, the magnitude of this momentum. Simplifying notation, we just drop the e index now. And we get dk, k to the 3, function of this k momentum times 2 pi squared, where this is the surface of the 4 sphere. Remember, it's the analogy to the 3 sphere, where we have this d3x. We have the integral, the surface over the 2 sphere ball, over the 3 sphere ball, which is 4 pi, and the integral over dr r squared. This is the simple transformation we can use for spherically symmetric functions in 3 dimensions. So we have basically a spherically symmetric function in 4 dimensions, in the 4-dimensional Euclidean space after the Wick rotation. So this is the trick to do these integrals more simply. And what we're gonna do here, we don't care about like the behaviors at low momenta. We really want the divergence behavior. So we expand the expression at large lambda over mass, where mass is the only other energy scale in the problem. Now we want to look at 1-to-1 and 2-to-2 amplitudes, and those will be relevant. Others will be actually not relevant for this discussion, as we will see shortly. First, let's look at the 1-to-1 amplitude. The Feynman diagram for this at one loop order. So we denote this as the one loop irreducible diagram, because it's irreducible because by cutting propagators we are still getting the same diagram. So the Feynman rules tell us we have negative I actually from here, because this is the I times the T is equal to I times the matrix element is equal to negative I lambda over 2 or negative I lambda times the loop momentum over the propagator. That comes from this Feynman rule that we have a closed loop here, and we have a symmetry factor d equals 2, as we discussed before. So we divide by 2, and then we divide through by I, which gives us a negative I here, and then this is the integral expression that we need to consider for this 1-to-1 amplitude. Now remember, Wick rotation gives us an I from the measure, so we get an I that cancels, that combines with the other I and the I from the propagator to give us a total minus sign without the I. The prefactor is lambda divided by 32 pi to the 4 from the measure, and the volume of the 2 sphere. We will use the volume of the 2 sphere momentarily. So then after the Wick rotation, we also use the surface of the 3 sphere to simplify the prefactor, and then we are left only with a one-dimensional integral here of the absolute momentum. Yes, we can simplify this integral, in fact, since k is positive, we can divide through by it, and then we get this integral here. And then let's say we are interested only in the behavior where the momentum cutoff is large, so we could expand this for large momentum k. If we look at this expression here, large k means this expression gets small. So if we call that epsilon here, so this epsilon small, we can Taylor expand this function, which is just 1 divided by 1 plus epsilon. And essentially for the epsilon being small, this is approximately given by 1 minus epsilon. Yeah, this is clear from this Taylor expansion that is equal to the value at epsilon equals 0, this 1, and plus the value at epsilon times the derivative of the function at epsilon equals 0. So that gives us minus 1 divided by 1 plus epsilon. At epsilon equals 0, it gives you just a minus 1. So you get 1 minus 1 times epsilon. This is the expansion of the function. And plugging this in here, we can just simply evaluate the integral and get the prefactor lambda m squared divided by 16 pi squared. And the integral here over k over m and m over k. Good. So we are finally left with a function defining this k over m as x. Yeah. So we are calling k over m x is a dimensional parameter. We can rewrite it like this, and then we have the definite integral over this expression is the x squared minus 2 log x evaluated between 0 and lambda over m. And so we see that there is logarithmic contribution and a quadratically divergent contribution to the function to the prefactor lambda m squared divided by 32 pi squared. So now we have regularized the leading divergence of this one-to-one amplitude, and we will see how to handle it later. The main thing is we have control over the infinity. Yeah, we know how it scales with growing momenta. That's the main message here. Now we have also quadratic. We have the quadratic and the log divergence. And we could have guessed it from just dimensional analysis that it should go this way. For example, here, this expression at large k goes like k, right? This goes like k cubed, this goes like k squared when the k is much larger than m. So this whole thing goes as k. The integrating k over dk gives us something like k squared between 0 and lambda. So that had to go as lambda squared at leading order, which we find and are happy. Good. Now we are looking also at the 2 to 2 amplitude, and there are three possibilities in this diagram. At higher order, the leading order would be just the leading order would be just a simple diagram like this with one lambda, but the next to leading order correction with lambda squared has one loop, but we can again write down the one loop irreducible diagram. Again, cutting propagators the diagram remains the same, so it's called irreducible. And we have this 4 different momentum assignments here. So we have a 3 different momentum assignments of this form. So we have a multiplicity factor 3. The disymmetry of the diagram is 2, as we said before. So we divide by 2. And the final rules give us, again, a negative I lambda squared now, with the integral over d4k divided by the propagator times the propagator squared, however, because we have 2 propagators instead of 1. So we have 1 divided by k squared minus m squared here, squared. And performing the same Wick rotational calculation gives us a logarithmically divergent term. This is also expected because we see this would give us would scale the numerator like k cubed. This scales like k. This scales like k to the 4 at large k. So integral 1 over k dk is proportional to log k. Still, it's not finite. It's an infinite expression at very large momenta, but it diverges only logarithmically, not quadratically. For us, it doesn't matter. Lambda in the limit lambda to infinity, the theory still seems nonsensical. So we have to do something with it. And the main part, what we did here again, is to parameterizing this infinity, putting the controlling cutoff, and we will see how to handle it soon. But now this is really a technical step just to introduce the cutoff and regularize the infinite integrals. Right. Now the next diagram of a 3 to 3 process at one loop irreducible with a one loop irreducible contribution to it has 3 propagators, as you see. If you take this, you have 1 over k squared minus m squared to the cubic power. This goes as k cubed. This goes as k to the 6. So the whole thing goes as 1 divided by k cubed dk. So integrating it from 0 to large lambda gives us actually 1 on k squared, right? So sending then k to lambda, we have something that goes like 1 over lambda squared, sending lambda to infinity. This expression goes to 0. So this 3 to 3 amplitude is 0, which is fine. And we will really see that this is very important, that this is well behaved, while the others can allow themselves to have some divergences. Just a quick comment by what which diagrams I mean when I say reducible. If we have the diagram like that, for example, it's a 2 to 2 contribution to the 2 to 2 amplitude, but this diagram is reducible because cutting the propagator would actually give us different types of diagrams with different loops and divergences. So this doesn't contribute to the 2 to 2 irreducible diagrams, right? So that's why the notation one loop irreducible, that was diagrams of this type, and that's it. That was just a comment on this property of reducibility or irreducibility. Okay, that is all there is about regularization. There are different techniques of regularizing infinite integrals, but the main point is that introducing this trick, we can make the expressions finite for a parameter that we take and control it, and we'll see how to have a well-defined limit of the theory where, while this cutoff, for example, goes to infinity, or any process where the regulator is removed, still by an intelligent construction of camels, by again adding and subtracting camels, we will manage to keep the theory healthy and well behaved while sending the cutoff to infinity. But that's the topic for the next lecture.